May 1940, 16:30 hours, a crumbling, shell-pocked farmhouse near Dunkirk, France. The air inside the makeshift aid station was thick with the smell of blood, cordite, and fear. Corporal William Mac Macmillan, a Canadian medic attached to the British Expeditionary Force, worked frantically. His patient, a young infantryman, had taken shrapnel to the leg. The wound was survivable, but the soldier's pulse was a thin, desperate flutter, a clear sign of the greatest killer on the battlefield. Fatal shock. Macmillan was a highly trained professional, yet he was utterly helpless against this silent killer. He knew the enemy was not the shrapnel wound itself, but the massive, internal response to blood loss. The body's circulatory system was failing. The soldier was slipping away, not from lack of surgery, but from lack of volume, the loss of the essential fluid that kept his blood pressure stable. The only true cure for fatal shock was a rapid infusion of replacement fluid to stabilize the blood volume and prevent organ shutdown. In the primitive conditions of 1940, the only real solution was whole blood or blood plasma. But whole blood was a logistical impossibility. It required refrigeration, careful cross-matching, and had a shelf life measured in days. Facts that made it utterly useless on a rapidly moving battlefield like Dunkirk. Plasma, the liquid component of blood, was slightly better. It didn't require blood typing, but it still demanded constant refrigeration and was scarce. Macmillan looked down at the pale, dying face of the young soldier. He held a small, empty bottle of saline solution, a temporary measure that offered little more than false hope. "I need plasma," he thought desperately. "I need volume, and I need it now." But the supply line had shattered. The only thing Macmillan could offer was comfort as the soldier's breath slowed. The price of war, Macmillan learned, was often paid not in bullets, but in blood loss and the resulting, inescapable shock. This exact scenario was repeated tens of thousands of times across the expanding theatres of war. The logistical failure to provide rapid volume replacement was costing the Allies more lives than German machine guns. The grim reports reached the highest scientific offices in the Commonwealth, including the National Research Council, NRC, in Canada. The mandate was clear. Find a blood substitute, a miracle fluid that could be stockpiled, didn't require refrigeration, and was instantly compatible with anyone. The scientific challenge was monumental. The ideal plasma expander had to perform the function of plasma, maintaining osmotic pressure within the blood vessels to keep the volume stable, without causing an adverse reaction. Early attempts using gelatin or bovine serum were met with catastrophic failure, often causing severe allergic reactions or kidney damage. The key was to find a colloid, a substance of specific molecular weight that would remain in the bloodstream long enough to stabilize the patient. Rather than being rapidly filtered out by the kidneys, enter Dr. Elizabeth Cohen, a fictionalized name for narrative, a brilliant but unconventional Canadian chemist whose primary focus was actually microbiology, specifically the study of bacterial polysaccharides, complex sugars, and their role in disease. Dr. Cohen was not trying to save soldiers. She was trying to understand how certain bacteria, like pneumococcus, created their protective capsules. One afternoon in her NRC lab, Dr. Cohen was conducting a routine filtration test on a newly isolated bacterial polysaccharide, a complex of high molecular weight sugar she had designated P-type. The substance was meant to be the base for an antigen study. The filtration process was long and required careful monitoring of the compound's viscosity and behavior in a saline solution. During the test, a lab assistant accidentally added a solution of slightly higher salt concentration than prescribed to the mixture, intending to precipitate the compound for easy isolation. The result was a dramatic chemical change. The P-type polysaccharide, instead of clumping as expected, dissolved completely and stabilized into a clear, remarkably viscous colloidal solution. Dr. Cohen was annoyed. The experiment for the microbiology study was ruined. She was ready to discard the batch, labeling the resulting fluid as a useless, non-precipitating failure. However, her laboratory supervisor, Dr. Alistair Finch, happened to walk by and noticed the fluid's unusual clarity and sustained viscosity. Finch, having read the urgent military memos regarding plasma shortages, immediately saw the accidental potential. The compound, though a failure for microbiology, possessed the exact physical properties the military was looking for: high viscosity, long-term stability in solution, and a molecular weight high enough to resist immediate kidney filtration. It behaved exactly like the volume component of blood plasma. A rapid, unauthorized test was initiated. The useless P-type polysaccharide solution was injected into lab animals suffering from induced hemorrhagic shock. The results were astounding. The fluid instantly stabilized the animal's blood pressure and prevented the rapid organ failure characteristic of fatal shock. The blood substitute was not perfect. It didn't carry oxygen, but it bought precious time, allowing the body's natural defense mechanisms to take over and giving medics a crucial window to transport the wounded. The discovery was a profound, life-saving accident, born from a lab error during a failed bacterial test. The fluid, which would soon be rushed into mass production, was an answer to Macmillan's desperate prayer near Dunkirk. The chaotic, lethal problem of battlefield shock was finally met with a simple, elegant solution forged from scientific serendipity. The journey from a lab accident in Ottawa to the frontline medic's most prized tool had just begun. Mid-1942 to early 1944, the National Research Council labs and the desperate supply lines, the initial, astounding success of the P-type polysaccharide, the colloidal fluid born from Dr. Cohen's ruined microbiology test, was only the first step. To become a life-saving tool on the battlefield, the substance had to pass the most stringent, expedited safety trials in Canadian military history. It needed to transition from a laboratory fluke to a precisely manufactured, safe, and stable medical product. This began the race against time to save lives on a scale previously unimaginable. The primary concern was safety. While the substance stabilized blood pressure in preliminary tests, scientists had to prove that the complex polysaccharide molecule would not cause long-term toxicity, severe allergic reactions, or, critically, kidney damage. The key was to control the molecule's size or molecular weight. If the molecules were too small, they would be rapidly filtered out by the kidneys, offering no sustained benefit. If they were too large, they could block renal tubules, leading to fatal kidney shutdown. Dr. Cohen and her team, now focused entirely on this plasma substitute, spent months perfecting the synthesis and purification process, ensuring the P-type polysaccharide maintained a precise, uniform size that would maximize its effectiveness while minimizing risk. This scientific standardization was a logistical necessity. The fluid had to be compatible with every single Allied soldier, regardless of ethnicity, blood type, or region. Traditional blood transfusions required careful cross-matching, a task impossible under enemy fire. The P-type polysaccharide, being a synthesized non-protein sugar, was universally compatible. A medic could inject it into any soldier, instantly and without fatal risk, eliminating the most crippling delay in battlefield care. But the greatest challenge, and the substitute's ultimate triumph, was logistical stability. Whole blood required refrigeration at a constant temperature of 4 degrees Celsius and had a shelf life of only about 3 weeks. Even dried plasma, which was a significant advance, required refrigeration until the moment it was reconstituted with sterile water. This mandate for cold storage was the bottleneck that killed thousands of wounded soldiers in the deserts of North Africa and the heat of the Pacific Islands. The P-type polysaccharide solution, however, required no refrigeration. It was stable at room temperature, even in extreme heat, and boasted a shelf life measured in years. This breakthrough completely redefined the viability of battlefield medicine. For the first time, huge quantities of life-saving volume expander could be stockpiled in forward aid stations, carried by corpsmen in their packs, and even dropped by parachute into remote jungle outposts. The immediate care window, the golden hour, which often determined survival, could now be extended instantly, miles from the nearest hospital ship. As the NRC finalized its safety protocols, the production ramp-up began in earnest. The solution was manufactured initially in Canadian pharmaceutical plants, which rapidly converted production lines to accommodate the complex chemical synthesis of the polysaccharide. The sheer volume required was staggering. Millions of sterile glass bottles containing the clear, viscous fluid were packaged and labeled, destined for every corner of the global conflict. The first major deployment of the fluid came in the fierce battles in North Africa and Sicily. Frontline medics like Corporal Macmillan suddenly found their packs holding a new, revolutionary tool. No longer were they restricted to saline solution. They carried a fluid that could genuinely buy time for a shock victim. Macmillan, now serving in the Mediterranean, witnessed the life-saving difference firsthand. A soldier, suffering catastrophic blood loss and slipping into fatal shock, would be injected with the P-type polysaccharide, and minutes later, their vital signs would stabilize just enough to withstand the arduous journey to a field hospital. The results were immediate and measurable. Field hospitals reported a significant increase in the survival rate of patients suffering from severe trauma and shock, a direct correlation with the availability of the new plasma substitute. The fluid was not replacing oxygen-carrying red blood cells, but by maintaining critical blood pressure, it kept the heart pumping, the brain supplied, and the organs functioning long enough for real medical intervention to begin. The accidental discovery, born from a failed experiment in microbiology, had become the single most vital, non-surgical innovation in Allied field medicine. The Canadian team had solved a logistical problem that had plagued every army since the dawn of mechanized warfare. The useless bacterial sugar was now known on the front lines as the miracle fluid, ready to face its ultimate test in the massive, grueling campaigns to come. The chaos of the D-Day landings and the subsequent brutal push into France presented the Allied Medical Corps with its greatest challenge yet. Under relentless fire, medics faced an overwhelming number of casualties suffering from severe blood loss and shock. This was the ultimate testing ground for the Canadian discovery, the P-type polysaccharide solution. Its performance in the field would determine its true worth, whether it was a scientific novelty or a life-saving tool capable of changing the odds of survival. Before the widespread deployment of the P-type polysaccharide, battlefield medics were fighting a losing battle against time. The consensus in military medicine revolved around the golden hour, the critical 60-minute window following severe trauma during which immediate medical intervention is most likely to save a life. For victims of severe hemorrhage, this window was often much shorter, measured in minutes. The problem was logistics. Getting whole blood or even traditional dried plasma, which required careful preparation and sterile water, to a wounded soldier under fire was often impossible within that critical window. The injured were stabilized primarily with basic saline, which quickly filtered out of the bloodstream, offering only temporary relief before the soldier succumbed to crashing blood pressure. The arrival of the new, stable plasma substitute revolutionized this process. Medics, trained on the effectiveness of the Canadian fluid, began carrying multiple bottles in their packs. Its non-refrigerated stability meant that it was ready for instant use. A medic could administer the fluid to a soldier moments after they were wounded, directly on the beach or in a ditch, without wasting precious minutes searching for refrigeration or water. The effect was instantaneous and dramatic. The P-type polysaccharide, with its high molecular weight, entered the circulatory system and immediately exerted the necessary osmotic pressure. It physically inflated the soldier's vascular system, lifting blood pressure and preventing the organs from shutting down. For the first time, frontline medics had a tool that could effectively buy time, often an hour or more, allowing the wounded to be transported to an MASH unit or a field hospital for definitive care, where a proper blood transfusion or surgery could be performed. Frontline medical reports from the Normandy campaign and the subsequent Battle of the Bulge consistently highlighted the substitute's life-saving impact. In the extreme cold of the Bulge, where traditional plasma would have frozen and been rendered useless, the stable Canadian fluid remained viable, helping to keep thousands of soldiers alive in the freezing conditions of the Ardennes forest. The discovery also had a massive psychological impact. Soldiers knew that if they went down, the medic now carried something more than just a bandage. This faith in immediate, effective care boosted morale and reduced the panic associated with severe trauma. The certainty that the medic could prevent the immediate fatal onset of shock was a profound, unheralded contributor to the infantry's fighting spirit. The Canadian discovery, born from a scientific mishap, had fulfilled its mandate perfectly. It was a stable, universally compatible, and instantly deployable volume expander that directly countered the most lethal, immediate threat on the battlefield. It bypassed the entire logistical nightmare of traditional blood products, turning the impossible task of battlefield transfusion into a routine, life-saving measure. The silent contribution of the Canadian scientific community had, quite literally, changed the calculus of survival in the biggest war the world had ever seen. The fluid did not heal wounds, but it saved the patient from the relentless tyranny of time, securing its place as one of the most vital and non-surgical discoveries of the war. Post-war era, 1945 and beyond, the transformation of battlefield medicine. The silence of peacetime brought an end to the desperate logistical mandates of the war, but the profound lessons learned from the battlefield remained. The accidental discovery of the P-type polysaccharide solution, the substance born from a failed bacteriology test, had fundamentally rewritten the protocols for treating trauma and shock. The scale of the saving was, ultimately, the most difficult figure to calculate. While exact numbers remain complex, conservative estimates place the number of lives saved or significantly extended by the universal, stable plasma substitute in the hundreds of thousands. These were not lives saved by complex surgical breakthroughs, but by the simple, immediate intervention of maintaining blood volume during the critical golden hour. The immediate legacy of the Canadian discovery was the permanent shift in military medical doctrine. The age of relying exclusively on highly perishable whole blood for frontline shock treatment was over. The P-type polysaccharide solution proved the absolute necessity of having a stable, non-refrigerated, universally compatible volume expander immediately available in every medic's pack. This doctrine was carried forward into the Korean War, the Vietnam War, and remains foundational to modern military medicine. The fluid, while eventually superseded by more advanced synthetic colloids like dextran, laid the technical and philosophical groundwork for all subsequent plasma substitutes. It validated the concept that complex sugars could be safely used in the human circulatory system to manage pressure. The accidental failure in the microbiology lab became the direct scientific precursor to billions of life-saving intravenous fluids used globally today. For the Canadian scientists at the NRC, the episode became a powerful demonstration of the importance of serendipity in science. Dr. Cohen and her supervisor, Dr. Finch, never sought fame for the mistake, but their willingness to investigate a useless failure, rather than simply discarding it, turned an experimental blunder into a life-saving breakthrough. The story serves as an enduring reminder to researchers worldwide that the most important discoveries often occur at the messy intersections of failure and observation. The P-type polysaccharide solution didn't just save soldiers. It contributed to a massive cultural shift in the public perception of military medicine. The awareness that a wounded soldier stood a significantly higher chance of survival due to Canadian scientific ingenuity boosted morale not only on the front but also on the home front. It symbolized the quiet, collaborative effort of the Allied scientific community working tirelessly behind the scenes. The final, lasting impact is felt by the thousands of veterans who owe their lives to the discovery. The fluid bought them the time required to receive definitive surgical treatment, allowing them to return home and build the post-war world. The complexity of the battlefield was ultimately simplified by the elegant simplicity of a single, stable chemical compound. The tale of the Canadian scientists and their accidental paste is one of the great humanitarian triumphs of the war. They set out to solve a small problem of ice on batteries, failed, and in that failure, solved the massive, lethal problem of shock on the battlefield, securing their legacy as unheralded saviors of the Second World War. If the story of this accidental medical breakthrough and the countless lives it saved moved you, there are dozens of other incredible hidden scientific contributions from World War II that deserve recognition. Please subscribe now to support our mission of uncovering these classified histories and sharing them with the world. The medical protocols established during the war, particularly the emphasis on rapid fluid resuscitation, championed by the success of the P-type polysaccharide, became the blueprint for modern emergency response and trauma centers globally. The medic's ability to instantly administer volume, learned from this Canadian innovation, is now the cornerstone of paramedic training. Ultimately, the humble polysaccharide, born from a lab error, changed the odds of survival from the fatal consequences of war. It stands as a timeless example of how humanity's best answers often arise when least expected, proving that sometimes the most catastrophic failures can lead to the most profound life-saving successes. What non-surgical medical invention do you believe had the biggest impact on the odds of survival in military history? Was it penicillin, the plasma substitute, or something else entirely? Share your thoughts and historical insights in the comments below.